All right, so we're gonna try to knock out some more of this first lesson. So we are into the portion of the section, or into the section of the lesson where we start talking about graphing position and time. So we've looked at graphing a little bit with that ping pong activity, and now it comes back with those ideas that we just got done talking about with kind of like distance and displacement and position. So the location of something as time goes by. That's what this graph is showing. And one thing that you can actually use the slope of the line to get on the slope of a position versus time graph is the average velocity. So this is a useful skill because we're gonna use velocity to describe motion as well. So we haven't quite learned velocity in any other way yet, except just by the name here. But you probably have a decent understanding just conceptually from your everyday life of what velocity is. So we'll rely on that. So this example, which is in this lesson and video, is also in D2L. So the worksheet that goes along with this is all right there. All these questions are there, so you can go back and refer to it. So so again, we're doing a position versus time graph. In the title of a graph, whatever comes first is on the y-axis, so that's the position over here. And we generally refer to position as x. And then the time portion, the second idea in the title, is on the x-axis. So so we have time, and it looks like we're counting by 2 or 1 for every line here. So 1, 2, 3, 4, 5, all the way up to 13, it looks like. And then we're counting by 10s going up on the position. And again, just to reiterate, this is not like climbing something up and down. This, if I was demonstrating this in class, I would be walking. So if you imagine sort of that number line again, if I started at 0, it looks like in 4 seconds of time, I travel 20 meters. So this first thing would be whatever that distance is, 20 meters. So that's positive 20, because these are all positive numbers up here. And then it looks like I stop at 20 for a while. So I'm stopped here for, it looks like from 4 to 6 seconds, I'm at 20 meters. And then it looks like I keep moving in that direction from 6 to 10, or 6 to, we'll just say it's 10. It's a little bit off. But from 6 to 10 seconds, it looks like I travel another 20. So I keep going in the same direction, another 20. And now I'm at 40. So this is like step 1, step 3. I'll put this as a 2 where I'm stopped. So 1, kind of 2, kind of 3, matching up kind of the motion with this graph. And then finally, the last part where from 11, it looks like, or 10 to 12 seconds, excuse me, it starts going back this way, and it looks like it stops pretty close to 20. So we're back there at the end of the thing. So I'll call that 4, and that would be this portion of the graph. So it moved back towards 0, so that would be moving to the left. So one of the first things like we just did is just to kind of look at a graph and feel out what it means. So don't necessarily just start jumping in and trying to figure out numbers and all that. It's just kind of getting an impression if this represents a real thing and motion and the position or location of an object as time goes by. We can use that to kind of get a feel for what's going on. So we started at 0, or the origin. We moved to the right 20 meters. Then we stopped for a little bit in section 2. Section 3, we moved to the right another 20 meters and ended up 40 meters away from where we started. And then once we got to 40 meters, we immediately turned around and came back to the 20. So that's sort of our motion there. So I'm going to take you through kind of going through this graph and answering questions about what's going on. So let's go ahead and do that. So for the first question, it says, what is the object's, I should have an apostrophe there, what is the object's position at 2 seconds? So if I go to 2 seconds on the time, you just go up until you hit the line, and then you go over. So the answer to this would be 10 meters. And if you wanted to say positive 10 meters, that's actually a better answer because it's a positive location. This is 0. These are all positive numbers. If we went the other way, which is possible, you could have negative position because that just means you move to the left. Or you're in a leftward or negative location. So we could have negative numbers here, but we don't in this first graph because I don't want to confuse you too much. At 6 seconds, same kind of work. I circle the 6 and I go up until I hit the line, and then I just go over and it says, okay, I'm at 20 meters. So the first 2 answers are 10 meters and 20 meters. And again, it's a positive 20. So that's just the location. So if you have a certain point in time, you should be able to read a certain position off for the value. the second one, second question says, at what times or time is the object at 20 meters? So we actually have several times when it's at 20 meters, and that's allowed. Like you're allowed to be at the same place at different times. So like when I wake up in the morning, I'm in bed. When I go to sleep at night, I go back to bed. So I'm in that location at different moments in time. That's allowed. But you can't be in multiple locations at the same time. So like I couldn't be at 6 seconds. I couldn't be at 20 and 10 and 30 unless I was really big. So I'm kind of highlighting here. That's location equal to 20. And I would say this one is also a location equal to 20. So this is sort of the opposite work. So instead of finding the time and then going up to the line and then going across, we're starting at 20 and we're just going across until we hit all those times. So it looks like there's that period of time where I'm stopped at 20 and this one instant of time when it is also at 20 at the end. So for 20 meters, I would say that's equal to times from 4 to 6 seconds and 12 seconds. So those would be the answers for 20 meters. If I was asking for 30 meters, which is the next question, what times am I at 30 meters? So we're going to look at 30 for our part that I sort of did the highlighting on before. So if I highlight, there it is. If I highlight 30 here and I go over wherever it hits the line at 30 and then I move down. So it looks like at 8 seconds. And this one looks like it follows at 11. So I would say 8 and 11 are your best answers for this one. So 8 and 11 seconds. So again, I think most of those skills are very practical, and you guys have those kind of already in your repertoire. So you don't have to do a lot of thinking about it. It's just kind of doing what you did. So the next part, I'm going to erase the stuff that's on the graph, and we're going to start talking about when is the object moving in the positive direction. So let's establish what the positive direction is. So again, in our number line kind of scenario, we've established directions as positive and negative. For all your math classes you've ever done, when you've done graphing, you've had kind of the XY axis. So this is like positive Y is up, negative Y is down. Positive X is to the right, and negative X is to the left. So the positive direction, this is representing something moving in the X direction, so we're going across here. Positive direction would be to the right. So anytime we think it's going to the right, we would list that time period because it's asking for when. And then when is it moving in the negative direction? That would be moving to the left. And if it's not moving at all, then the object would be stopped. So we've already kind of drawn this picture out. Let me just start over again with the drawing. So we started at 0, and then we went to positive 20. So positive 20 here. That was the first kind of portion of the graph. So I'll put a 1 there. Then for portion 2, it looks like we're stopped. So I'm just going to draw a line here for portion 2 that we're stopped at. And again, I'm just using some colors to help make it stand out a little bit better. It's moving to the right again, and it moves another 20, so it goes to positive 40. And that's for section 3 of our graph that we've outlined already. And then finally for section 4, it moves back that way to the left because it starts at 40 and it ends up at 20. Okay, so so anywhere that's moving to the right would be, I think, sections 1 and sections 3. So positive direction moving to the right would work. So it looks like it's moving to the right from times equal to 0 to 4 seconds. That's the first time interval. And then from, it looks like 6 to 10 seconds or so. Again, the graph's a little bit off, but don't worry about it too much. It should end up at a whole number. You don't have to worry about like a fraction of a second or anything like that. Moving to the left would be the last section, which I didn't label up here, but it's like section 4 here. So the line moves back down. That's moving to the left in our instance here. So left would be from that 10 seconds to 12 seconds. And then finally stopped is just section 2. So when it's stopped, that's 4 to 6 seconds. Okay. So so those are the answers to number 3 with the directions and what's going on there. So again, I don't think that's overly challenging, but you just have to think about kind of the motion and what this is showing you. And if you draw a little number line, I think that's a good way to kind of establish direction and whether it's moving positive or negative or stopped or however. Total distance traveled, total displacement, that's the next part. So total distance, again, just to review what we did for total distance in the previous video. Total distance is just equal to the distance in section 1 plus the distance in section 2 plus the distance in section 3 plus the distance in section 4. So however many sections you had, however many steps you take, you just add them all together. Again, you don't worry about whether you're going right or left or up or down. It's just kind of putting those values together. So if I was writing this out, D1, I think it's 20 because I go 20 here. Then it's nothing because I stopped. I stayed at 20. Then it's another 20 from 6 to 10 seconds. And then finally, there's another 20 from 10 to 12. So if I add up 20 plus 0 plus 20 plus 20, I get 60 meters total. That is the total distance. Displacement is different, okay? The displacement is, again, the change in position, and it includes direction. So whether it's going left, right, up, down, positive, negative. And again, the equation for displacement, and I'll try to get this written out the right way so I don't confuse anybody with my handwriting with a triangle. So it's change in x equals x final minus x initial. So the final position of this whole thing is at 20. And it's at a positive 20 because that's its location. So I end up at positive 20. And I'm going to subtract off the initial position, which was at 0, because that's where the line started at. So 20 minus 0 is a positive 20. So the answer to this, or what that means, it means it moved 20 meters to the right. So that's the overall displacement from where it starts to where it finishes. It's the total. It doesn't matter that it went 20 and then stopped and then another 20 went and then came back to 20. It just cares about from where it started to where it finished, okay? So those are just kind of reviewing distance and displacement. Again, big direction, or the direction is the main difference between those two elements, where distance, you're just adding stuff together, and displacement, it matters kind of the direction that you're headed. And then we want to find average velocity. So on the previous slide, we talked about average velocity. That is the slope of the line. So hopefully you guys feel comfortable finding slopes. I'm going to kind of look at the slopes for these different time periods. So 0 to 4, 4 to 6, 11 to 12. And again, it'll, I think, help you better understand what velocity is too. So let me get rid of that for a second. So again, the slope, or the formula for slope of a line is just the change in y over the change in x. So it's the rise over the run. That's the way that I express it. So rise divided by run. So you move up and then you move over. So I'm just measuring like how much it rises or falls as to how much it goes over. So looking at the slope of this first line, I could say that it goes up from 0 to 4 seconds. So wait, what? From 0 to 4 seconds, it goes from 0 to 20. So that's a positive 20 because it goes up 20. If it went down 20, we'd put a negative 20. So it goes up 20 meters, and I'm going to divide that by how much time goes by, which is the run, because run is measuring the x-axis here, and that's 4 seconds. So if I did positive 20 divided by 4, I have a positive 5 meters per second. And that is the correct answer for this first segment of time. And if it makes sense, right? So like if I start out at 0 and I go, in 1 second, I go 5 meters per second. So every second that goes by, I'm moving plus 5 meters. So I'm going to go from 0 to 5 to 10 to 20, and that's 4 seconds of time going by. So that's what we're talking about for that. From 4 to 6 seconds, that is the next section that we're going to look at. So this horizontal line. You might know the slope of a horizontal line. It should be 0, but you can always figure it out using the slope formula. So if it doesn't go up or down, there is no meters. It goes no meters. It's not going anywhere. So it's 0 meters in it looks like 2 seconds, because from 4 to 6 seconds is 2 seconds of duration. So 0 divided by 2, that's just 0. So it's 0 meters per second. If you're going 0 meters per second, that means you're stopped. And that is what we said happened at that point. So from 4 to 6 seconds, that's where the object stopped, and that makes sense. Our math follows that up. So again, velocity is sort of telling you how much you're being displaced in the amount of time that you have to move. So it's sort of the rate of displacement. We'll get into that definition in a little bit, but this should help you kind of understand it better when we get to that point. We'll keep going through this. So we got 6 to 10 seconds is the next section of time. So from 6 to 10, we started at 20 here, and we went up to 40 there. So that's another plus 20. And from 6 to 10 seconds, that's 4 seconds of time. So this is the exact same slope. It's a positive 5 meters per second. So this line matches this line in terms of its slope. Finally, the last one is from 10 to 12 seconds. And it looks like it's starting at 40 and going to 20. So that's moving negative 20. The line's dropping 20 meters. Let me put a meters up here. I left it out. And then that's happening from 10 to 12 seconds, which is 2 seconds. So if I look at that, if I take negative 20 divided by 2, I get a negative 10 meters per second. And that is the velocity of the object. Again, the negative tells you the direction, so it means it's doing at my smart notebook's freezing up, so let me wait a second on it. But it's moving negative 10 meters per second, so it's going to the left. There we go, maybe. It's there we go. Yeah, let's get that. Sorry about that. It's going left at 10 meters every second. So that's what it means by meters per second. You're probably familiar with like miles per hour. So it's the same kind of measurement. It's just slightly different in terms of like it's talking about you're going miles in an hour instead of meters per second, but it's still dealing with a displacement over a time. And that's what the slope is. So if you look at this, the slope is the change in position, which we just got done talking about, and we called that displacement, divided by the change in time. So if you take the change in position or the change in displacement, or I'm sorry, change in position, which is the displacement, divided by the change in time, you get the velocity. So that is our kind of first working through a graph and understanding what's going on there. Now, I think that's all the questions I had, and yeah. So it's just, again, you're dividing the displacement by the time. Okay, so that's that graph, and let me jump ahead to speed and velocity. So the difference between this technical difficulties, sorry. The difference between distance and displacement is the same as the difference between speed and velocity. So like if you understand the difference between those concepts, it'll make it easier to understand the difference between speed and velocity. So in everyday life, everybody kind of, in your normal everyday life, you would use these two words interchangeably. You would just say they're synonyms. So speed, sort of how fast something moves. Velocity is how fast something moves in everyday life. In physics class, there is a different meaning for those. So speed is how fast something moves, or the rate at which distance is covered. So that's the key element here, that that speed uses distance. Okay, so distance is the point there. You're very familiar with speed, miles per hour, kilometers per hour. We're going to use meters per second here because that's the units that we use. All of these measurements involve distance and time. In your car, you have a device called a speedometer or a speedometer, and that speedometer tells you how fast you're going at a particular moment in time. So it's just calculating that for you. Velocity is different. Okay, so velocity tells you how quickly an object changes position. So that is the real difference between two. It's how quickly, so that's a time. So it tells you how much position you change with time, and change of position, again, is displacement. So that displacement idea is different than that distance idea. And that is really the big kind of distinguishing feature between those two. Again, velocity is a vector, so direction is important, okay? So some examples of velocities, meters per second, 10 meters per second north. You can read these, but it's the same kind of concept of you have something moving, there's a rate, and now you have this unit. So when you say the velocity, you're including a direction. It also could be, if you're saying up, you could say positive 30 meters per second. So like those, it doesn't have to be a formal direction or a word for it. It can be positive or negative, and that indicates an idea in our problem. Okay, so again, velocity is a vector. It's described by a measurement, a unit, and a direction. And then a scalar is a quantity described by a measurement only, so it's just your unit and your number. So again, these are nice because V and S and S. So if you're asked a question about them, you can hopefully remember those when you're taking your test. Okay, so let's go ahead and try to knock out this example, and I'll probably pause there, and then we'll do the last graph for the lesson, and we'll get into that. So this one reads, man walks in from his house to the store, to the post office, then back to the store. So same example, the entire trip takes a half an hour. So that's 0.5 is a half, so 0.5 hours. And we want to know the man's average speed and the average velocity for the entire trip. So if we calculate speed, it's the total distance divided by the total time. So the total distance, he goes house, store, post office, so that's 6, and then back to the store, so that's 12. So again, sorry, not 12, that's 9. So 3 to 6, and then back to the store, that's only 9. I wrote the wrong number. And you can't read it well anyway, but I'll try to fix it. So that's 9. And then we're going to divide by that time, so that's a half hour. So if you divide 9 by a half, if you put that in your calculator, that's 18. All right, so that's 18 kilometers per hour, which is faster than what a real person can do, but it's okay. We have a fast person. So total distance divided by a change in time, and that's what this is going to show here. Okay, for the displacement or the average velocity, you got to calculate the displacement. So what's the displacement of this person if they go from his house to the store, the post office back to the store? It's really just from the house to the store, right? So it goes from the house to the store. So that's going to be a +3 for the displacement. So that's the change in position, or delta x. And then we got to divide it by the time to get velocity. So if I do that, +3 divided by, and that would be meters, or I'm sorry, kilometers. Okay. Divided by 0.5. So again, if you divide by half, that's the same as multiplying by 2. So that's 6, and it's a +6, +6 kilometers per hour. So that sort of makes sense. If they go 3 kilometers in a half hour, they should go 6 kilometers in a full hour. So so that's what we're calculating there for the velocity, and that is going to be worked out here. And I think it's on your sheet there too, if you printed out your notes. So you could say +6 kilometers per hour. You could say 6 kilometers per hour towards the store. But you can see again that these are not the same thing because they are measuring different ideas. So again, speed deals with the entire distance traveled. Again, velocity deals with the displacement. So it's just from where you start to where you finish. Also, it's sort of like the idea that you're gonna go from just one point to another, and it doesn't care about like you passed the store, you went to the post office, and you came back. it just wants to get from this point to this point in the same time. So like if this person was walking and they did all that walking back and forth and back and forth, when they got to the store and it took them that amount of time, it's going to be going at this rate that's slower to get there in that amount of time. That might have been a little confusing, but it's not that. You just stick to the formulas and make sure that you go with the difference between total distance and displacement. All right, so I'm going to pause there, and I'll probably edit out some of that other stuff. But we'll pause there, and we'll pick this back up.